Have you ever wondered when menopause might happen for you? Or perhaps you're planning your family and want to understand how your reproductive timeline might unfold. These are incredibly important questions, and for a long time, the answers felt shrouded in mystery. But what if I told you that science is rapidly advancing, offering new and more precise ways to predict this significant life transition? Welcome to my channel, where I break down complex health topics into clear, evidence-based information you can trust. Today, we're diving deep into the fascinating world of menopause prediction. We'll explore everything from the traditional methods your grandmother might have heard about to the cutting-edge scientific approaches that are emerging right now. My goal is to empower you with knowledge, helping you understand the science behind predicting menopause timing so you can make informed decisions about your health and future. Let's get started. For generations, predicting menopause was largely based on anecdotal evidence and a few basic indicators. Let's start with the most common one. Family history. It's often said that you'll go through menopause around the same age as your mother or older sisters. And there's some truth to this. Genetics play a role in determining your reproductive lifespan. If your mother experienced menopause early, there's a higher chance you might too. However, family history is a general guide, not a precise predictor. It doesn't account for individual lifestyle factors, environmental influences, or unique biological variations that can affect your personal timeline. As science advanced, we started looking at hormonal markers. The two most commonly discussed are follicle-stimulating hormone, or FSH, and anti-Müllerian hormone, or AMH. FSH is a hormone produced by your pituitary gland that stimulates the growth of follicles in your ovaries. As you approach menopause, your ovaries become less responsive to FSH, so your body produces more of it to try to stimulate them. This means elevated FSH levels can signal that menopause is approaching. FSH levels begin to rise as early as 6 to 10 years before the final menstrual period, with an accelerated rise approximately 2 to 3 years before menopause. However, FSH levels can fluctuate significantly throughout your menstrual cycle and even day to day. This variability makes it less reliable for early prediction. It's more of a late-stage indicator, showing significant changes closer to the actual menopause transition. Now let's talk about AMH. This is often considered the most validated and widely used biomarker for assessing ovarian reserve, which is essentially the number of eggs remaining in your ovaries. AMH is produced by small follicles in your ovaries, and its level generally declines as you age and your egg supply diminishes. AMH provides an earlier and more consistent signal than FSH. Studies show that AMH levels start to drop several years, sometimes up to 7 to 10 years before the final menstrual period. A lower AMH level correlates with approaching menopause, and specific thresholds, for example, below 0.5 nanograms per ml, can predict menopause within several years with reasonable accuracy. While AMH is a powerful tool, it's important to understand its limitations. It primarily reflects the quantity of your ovarian reserve, not necessarily the quality of your eggs. And while it's a good predictor at a population level, providing estimates for groups of women, it still has limitations for predicting the exact individual timing of menopause. The prediction window can be broad, and individual biological differences can influence the precise timing. While traditional methods provide valuable insights, recent scientific advancements are pushing the boundaries of menopause prediction. Researchers are now looking at more complex models that combine various biomarkers and even delve into our genetic makeup. Instead of relying on a single hormone, scientists are developing combined biomarker models. These models integrate multiple biochemical, hormonal, inflammatory, and metabolic markers to provide a more comprehensive picture of ovarian aging. For instance, beyond AMH and FSH, studies have identified other circulating protein biomarkers significantly associated with early menopause, such as resistin, adrenomedulin, adipsin, IGF-BP1, and apolipoprotein A1. These proteins are linked to inflammation, fat cell signaling, and neurohormonal pathways, offering additional clues about a woman's reproductive trajectory. Combining these markers with machine learning approaches significantly improves the accuracy of predicting menopause timing and ovarian function decline. For example, a 10-year risk prediction model using clinical and lifestyle factors like age, alcohol consumption, smoking, education level, and systolic blood pressure has shown good discrimination in predicting natural menopause onset. This means that by looking at a broader range of biological indicators, we can get a much clearer and more personalized forecast. Our genes also hold clues about our reproductive future. Bioinformatic approaches have identified specific hub genes related to immune response regulation and inflammation, such as TYROBP, RAC2, CD14, and ZAP70, that are implicated in ovarian aging. This suggests that our immune and genetic predispositions may play a role in how our ovaries age. While genetic testing for menopause prediction is still an emerging field, understanding these genetic markers can lead to personalized strategies for fertility preservation and improving ovarian health based on an individual's unique genetic profile. It's a fascinating area of research that promises to unlock even more precise predictions in the future. Beyond traditional hormones and genetic markers, the frontier of menopause prediction is now venturing into the realm of omics, specifically proteomics. This is where the science gets truly exciting, offering a glimpse into the future of personalized health. Imagine a clock that doesn't just tell time, but tells your biological time. That's essentially what proteomic clocks aim to do. Instead of looking at DNA, our genetic blueprint, or RNA, the instructions for making proteins, proteomic clocks analyze a vast array of proteins circulating in our blood. Proteins are the workhorses of our cells, and their levels and modifications can reflect the real-time physiological state of our bodies, including the aging process. Proteomic clocks measure biological age using composite protein signatures that reflect systemic physiological and molecular aging processes, including inflammation, oxidative stress, and metabolic changes. A pilot study found that proteomic age acceleration correlated with lower AMH levels and lower oocyte yield, indicating that proteomic clocks capture aspects of ovarian aging beyond just follicle count. They may reveal fibroinflammatory and metabolic changes in ovarian tissue relevant to reproductive aging that AMH alone does not capture. Proteomic clocks are part of a broader family of biological clocks that aim to measure our true biological age, which can differ significantly from our chronological age. Check out my earlier video series about this topic. Two other prominent types are epigenetic clocks and glycomic clocks. Epigenetic clocks analyze changes in DNA methylation patterns, which are chemical tags on our DNA that influence gene expression without changing the underlying genetic code. Epigenetic clocks like the Horvath clock or Grimm age clock have shown promise in assessing general biological age and even ovarian aging, correlating with markers like AMH. Some specialized epigenetic clocks, like the granulosa cell clock, are even tailored to ovarian tissue samples for improved prediction accuracy. Next, glycomic clocks. These focus on the glycome, which is the entire set of sugars or glycans attached to proteins in our body. Glycosylation of immunoglobulin G is an important regulator of the immune system and an important contributor to inflammation. Sex hormones are a key regulator, and a recent RCT using IgG glycans as a biomarker demonstrated that supplementing with estrogen slowed down biological age. Changes in IgG glycome composition, for example, became detectable several years before the final menstrual period, particularly during the perimenopausal transition. These changes reflect declining estrogen levels and increased systemic inflammation, making them promising early biomarkers for anticipating the menopause transition. Think of it as the hemoglobin A1C equivalent of average blood glucose measurements. While all these clocks offer valuable insights, proteomic clocks have the potential to detect earlier or more subtle changes of ovarian aging through systemic biological aging metrics. They are still under development and require large studies for validation and clinical implementation in ovarian aging forecasting. It's crucial to understand the distinction between ovarian aging and systemic biological aging. While they are interconnected, they are not always the same. Ovarian aging refers specifically to the decline in the quantity and quality of eggs within the ovaries, leading to a decrease in fertility and eventually menopause. It's a localized aging process driven by factors unique to the ovary, such as follicle depletion and changes in the ovarian microenvironment. Systemic biological aging refers to the overall aging process of the entire body, affecting all organs and systems. It's influenced by a multitude of factors including genetics, lifestyle, environmental exposures, and chronic inflammation. General biological clocks, like many proteomic or epigenetic clocks, aim to measure this broader systemic aging. While ovarian aging is a component of systemic biological aging, it can sometimes proceed at a different pace. For example, a woman might have excellent overall health in a young biological age according to a systemic clock, but her ovaries might be aging more rapidly due to specific genetic predispositions or environmental factors. Conversely, someone might have signs of systemic aging, but their ovaries are still functioning well. Understanding this distinction is key to developing targeted interventions and personalized predictions. So, why does all this cutting-edge research mean to you? The ability to predict menopause timing with greater accuracy has profound implications for women's health, family planning, and overall well-being. For many women, understanding their reproductive timeline is crucial for family planning. Knowing approximately when menopause might occur can help in making informed decisions about when to start a family, whether to pursue fertility treatments, or consider options like egg freezing. While AMH combined with age is currently the best hormonal predictor for time to menopause, it offers good population-level estimates, but limited individual precision. This means it can tell a group of women, on average, when they might expect menopause, but it's less precise for a single individual. The prediction is more reliable as women approach menopause, but less so many years in advance. For example, women with low AMH levels aged 45 to 48 might have a median time of about 6 years to menopause, whereas younger women 35 to 39 with the same AMH might have around 10 years. This highlights that age is a critical factor alongside AMH. The goal isn't to give an exact date, but to provide a more informed window, allowing women to plan their lives with greater confidence. Menopause isn't just about the end of fertility. It's a significant hormonal shift that can impact various aspects of women's health. The decline in estrogen levels can affect bone density, cardiovascular health, cognitive function, and mood. By having a better understanding of when menopause might occur, women and their healthcare providers can proactively manage these potential health changes. For instance, if a woman is predicted to enter menopause earlier, her doctor might recommend earlier bone density screenings or discuss strategies to maintain cardiovascular health. Studies have shown that inflammatory markers and metabolic biomarkers change with menopause transition and are associated with ovarian aging. Including these markers alongside ovarian hormones like AMH and FSH is a promising avenue to improve predictions of time to menopause and related metabolic health risks. This holistic approach allows for more personalized preventive care and health management strategies. I want to reiterate the importance of differentiating between population-level predictions and individual-level predictions. Most of the current tools, even advanced ones, provide probabilistic predictions. This means that they tell us the likelihood of menopause occurring within a certain time frame for a group of women with similar characteristics. They are not yet able to pinpoint the exact date for an individual. While AMH combined with age improves prediction accuracy compared to age alone or AMH alone, individual predictions remain imprecise, especially when menopause is not imminent. Variability in AMH decline rates, individual biological differences, and external factors all influence the timing, reducing exact prediction accuracy. The accuracy improves closer to menopause when AMH levels becomes very low or undetectable. Therefore, clinical use is best focused on risk estimation and counseling rather than exact individual age prediction. The ongoing research into proteomic clocks and other multi-biomarker models aims to narrow this prediction window and provide more personalized insights. However, for now, these tools are best used as guides for risk assessment and proactive health planning rather than definitive timelines. We've covered a lot of ground today, from the traditional methods of predicting menopause to the exciting new frontiers in scientific research. We've seen how family history and hormonal tests like FSH and AMH provide valuable, though sometimes limited, insights. We've also explored how combining multiple biomarkers and delving into genetic markers can offer a more comprehensive picture. And looking into the future, proteomic clocks represent a truly promising direction, offering the potential for highly personalized predictions by measuring our biological age at a molecular level. Understanding the differences between ovarian aging and systemic biological aging helps us appreciate the complexity and individuality of this natural life transition. Ultimately, the goal of all this research is to empower women with better information, allowing for more informed decisions about family planning, health management, and overall well-being. While precise individual predictions are still evolving, the ability to assess risk and plan proactively is becoming increasingly sophisticated. If you found this information helpful, please share this video with other women, friends, and family who might benefit from understanding these evidence-based methods for predicting menopause. Knowledge is power, and by sharing this information, we can help more women navigate this important life stage with confidence. Don't forget to subscribe to my channel for updates and hit that notification bell so you don't miss my next video. I love hearing from you, so please leave your questions and comments below. What are your thoughts on menopause prediction? Have you used any of these methods? Share your experiences. Thank you for watching to the end, and I'll see you in the next video.